In the last episode, I went over the control of the various registers in the CPU and demonstrated moving data into and out of the data bus, as well as moving data between the registers. Today, we dive into the workhorse of the CPU, the ALU, or arithmetic logic unit, where all the math and logic functions will happen. Stay tuned as we start with a 4-bit ALU with 4 functions and also adding the carry and 0 flags and show its operation. Then we'll add it to the CPU design and test it, so stick around. Have you ever wondered how you can make your own CPU or microcontroller? Have you ever been curious about field programmable gate arrays, also known as FPGAs, but find them to be mysterious black boxes? Or wish you had a microcontroller-like device with a larger memory address or wider data bus? Well, stay tuned as we delve into the world of FPGAs and create a CPU and eventual microcontroller from scratch. Hello and welcome to 100 Random Tasks. I'm your host, Philip Lett, and if you like what you see here, please give us a like and leave a comment. And subscribe if you want to be notified when more videos are uploaded, and it would really help the channel. With that, let's do some math. Once again, I've started a new project, ALU testing, and added the usual files. Here I have the verilog file for the ALU, and it takes 3 inputs and 3 outputs. You'll also notice that there is no clock input. That's because the ALU output will change whenever the input changes. It's asynchronous. This will be important to know later for the flags. The A and B inputs being 4 bits wide, which the ALU will perform the operations on. The O output is also 4 bits wide, which will have the result of the operation. The carry and 0 flag outputs, and the 2-bit select line input to choose which operation to perform. The output and carry are designated registers since they will be used in the always block. But the Z flag is not, and this is because it will be set using an assign statement below, outside of the always block. You'll also notice that there is another register declared in the module called internal and is 5 bits wide. This is needed as a temporary place to put the outcome of the operation before setting it to the output. If you remember your binary math, the reason for the 5-bit variable is that when you add or subtract 2 4-bit binary numbers, it is possible for a 5-bit result. In the example I have here, there is 1010 plus 0111, or 10 plus 7. If you do the binary addition, the result is 10001. Or 17. So bit 5 stores the carry flag for us, which we can pass out of the ALU. In the module is the usual always block, and the sensitivity list is the asterisk, meaning that the block will fire if any input changes. Then I have a case statement dependent on the select lines. And in each case, the result is first passed to the internal variable for the reasons mentioned earlier. The 4 operations are add, subtract, logical and logical or. The default case will just set the value to 0. This is just good practice to add, but shouldn't ever fire since we have all 4 possibilities covered. Beneath that is where the output is set, using curly braces to create a 5-bit output since the internal variable is 5 bits. The O output receives the lower 4 bits of the internal, and the C output receives bit 5 of the internal value. If internal happens to be 10001, then the carry flag is 1, and the O output is 0001. Finally, the Z flag is determined using an assign statement, which essentially creates combinational logic for the output. Here we are using the question operator. This says that if O equals 0, set Z to 1. Otherwise, set Z to 0. It's ignoring all the O bits together. If they are all 0, the output is 1. If any bit of O is 1, the output is 0. The beauty of this file is that to add additional functions, all that is needed is to change the select bit width and add the additional cases. With 3 select lines, 8 functions are possible. With 4, 16 functions, and so on. Later in the series, there will be additional functions, but for now, we'll keep it at these 4. After creating the schematic symbol and adding it to the top level, I added the I/O markers and set up a pins constraint file as always. From that, I'll wire up 2 4-bit dip switches for A and B, 2 wires for the select lines, and 6 LEDs. 4 for the output, and 2 for the flags. Let's wire that up. Here's the ALU programmed, and by now you should know how to get to this point. If not, you can check out earlier videos to see how it's done. I'll leave links to those videos in the description below. The first LED is a carry flag, followed by the 4-bit output, and on the end is the 0 flag. Right now the select lines are 0, 0, selecting the add function. Both A and B are set to 0, so the output is also 0, because 0 plus 0 is 0. And there is no carry, so it's also clear. And because the output is 0, the 0 flag is a 1. If I go back to the addition example from before and set A to 1010 and B to 0111, the output becomes 0001 with the carry flag set. Since the result of that addition is 10001, with the output not equal to 0, the 0 flag becomes clear. If I set A and B to 1000, the output becomes 0. The 0 flag is set, and the carry flag is set, since 8 plus 8 is 16, or 10000. Going back to the original numbers, if I now select subtraction, the result is 3 as expected, because 10 minus 7 is 3. Going to the AND function, the result is 0010. And the OR function is all ones. In all these cases, the Z flag and the carry flag are clear. Going back to the AND function and setting A to 1000 and B to 0111 sets the output to 0 and sets the Z flag, since if you AND A and B together, that output ends up being 0. With the ALU working as expected, now we can add the 8-bit version to the CPU design and test it with the accumulator. Looking at the outline, the A input is the output of the accumulator, and the B input comes from the internal data bus. So all operations use the accumulator as one input, and the other can come from another register or external memory. Also added are the flags. Remember earlier when I mentioned that the ALU outputs change whenever any input changes? In order to save those values, it's necessary to have a 2-bit synchronous register to store those values. This will be the same as the other registers, with the exception that it will only be 2 bits wide. Let's go ahead and add the ALU to the schematic, as well as the register to store the flags. Back to the CPU again, and I've added the ALU verilog file and copied the code from the test project. A few changes were needed, namely setting A, B, and O to 8 bits, setting the internal value to 9 bits, and setting the default case to 8 bits. Those are all the changes that are necessary, so from that we'll create the schematic symbol. In the main schematic, I'll delete the temporary connection to the accumulator and place the ALU, then make all the other connections. With the ALU now added and connected, I'll make the flags register. Change our outputs to reg again, and start our code. Oh, I forgot one thing. We also have to have our load pin. That way we can tell the register when to load. And that's it. Let's check our syntax. And I forgot the brackets around our sensitivity list. And the second end for our always block. Okay, now we're good. So we'll create our schematic. And add it to our top level. Okay, and there we go. With the ALU and flags register wired up, we can now add the I/O markers and test that if it works. So let's do that now. I only need a few of the control lines, namely the ALU select lines, the accumulator load line, the flag load line, C out, and Z out, as well as the select lines for the MUX, the memory output enable line, the clock and reset lines, and the data bus. And the rest of them I can go ahead and delete. With that done, I can now wire up the test circuit with the transceiver as before, only using all 8 bits. The board is programmed, and I have the control lines labeled. The leftmost two are the mux, and for this test, only 0, 0 for the accumulator and 1, 1 for external memory is needed. The next two are the ALU select lines for the function. The next is the accumulator load line, and lastly is the flag load line. Finally, on the far left is the read-write line. Right now, all lines are low except for the read-write line, which is in write mode, with the mux lines selecting the accumulator. So the value of the accumulator is shown on the 8 LEDs. This also means that the A input to the ALU is 0, but so is the B input since the accumulator, which is 0, is on the internal data bus. So that means the output of the ALU is 0. But shouldn't the 0 flag be set? The current status of the flags first needs to be loaded into the flag register by the clock. So if I cycle the clock, the 0 flag should be set. Nothing happens because the flag load line is 0. If I set it to high and cycle the clock, now the 0 flag is set as expected. Now let's do an addition. I want to load the value 1 into the accumulator. To do that, I'll set the read-write line to read, and set the dip switches to 1. That value is now displayed on the LEDs. Next, I set the mux to 1, 1 to select external memory, leave the ALU function at 0, 0 for addition, and set the accumulator load to 1. Now if I cycle the clock, 1 should be loaded into the accumulator because A input is 0 and the B input will be 1. Added together results in 1 stored in the accumulator, and the 0 flag should be clear. The 0 flag cleared as expected, and now if I set the mux to 0, 0 for the accumulator, and the read-write to write, the same value should be shown on the LEDs. Perfect. Now let's add the accumulator value to itself. For that, we don't need to change anything. The mux is already pointing to the accumulator, so input A and B are both the accumulator value, and being in write mode shows what's currently on the accumulator on the LEDs. Now if I cycle the clock, it should double each time. 1 plus 1 is 2, 2 plus 2 is 4, and so on. So the LED should move to the left until the carry flag is set, at which point it stops, because the accumulator will be 0, and because it's adding to itself, the result is 0. And the 0 flag should also become set. I'll cycle the clock and see if that happens. And sure enough, it does. So this proves that the ALU, the flags, and the accumulator are working properly. I could test the other functions, but this video is getting long enough as it is. So if you're following along, I encourage you to try the other functions on your own. I'll leave it there for now. In the next video, I'll dive into the heart of the CPU and look at the control block which takes the instruction and coordinates all the actions at the right time. This will probably entail more than one video to cover, but once we're done, we should have a finished, usable, simple CPU that will run instructions from external memory. So subscribe and hit the notification bell so you don't miss it. And if you like these videos, consider becoming a patron to show your support, so I can continue to make videos like these. I'll leave a link in the description below. And if you've made it this far in the video, thanks for watching.